Howdy ho, AS Math neighbors. It's your boy, Mr. Knight, bringing the gospel of math to your doorstep. We are really knee-deep in trigonometry right now, and we need to just kind of take a step back for a second. We've gone through all of the trig that we're going to need to go through, so hallelujah, you're through it. But there's a lot of you guys that are kind of in different spots with your trig. There are some things you're struggling with that others might not be, and so I kind of want to capture that and get you back on track. We're going off on a tangent, if you will. Okay, so these problems, these are not study guide problems. These are just problems that help us get back on track. Okay, and they also include an answer key on the back. And they also include after each section. After each section, it'll rate your comfort level and give me a comment being more specific on what you're struggling with. And that's invaluable feedback to me and to yourself as a result. You can be honest with yourself, okay? So let's run through these problems. We'll look at number one. We're giving the following angles as positive angles. So I'm going to use a simpler example. I'm going to say I'm going to have negative 10 degrees, okay? And if I go, in the clockwise direction, that's negative, so I'll end up at negative 10 degrees. But if I want to go positive, I got to go counterclockwise. I would end up at positive 350 degrees. So those angles, we haven't used this vocab for it, but it might be a good idea to call these guys coterminal angles. They're just angles that end in the same location. So if I say the coterminal angle of negative 10 degrees, it would be 350 degrees, okay? And all we got to do to go from a negative angle to a positive is just add 360 degrees on the circle, and you'll end up coming fully back around. You can keep doing that and get more terminal angles, coterminal angles, but we just need to make these guys positive, and that's it. Okay. Number two, it gives you a triangle PQR, it gives you some side lengths, and it just wants you to write down the values for the trig values. So you know that sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, ka, and then toa, tangent, is opposite over adjacent. You can use those to help you. And when you have a triangle and you're trying to construct it, your hypotenuse, which is always across from your right angle, it's always going to be your longest side. So whatever your longest side is, so like PQ, that's going to be my hypotenuse right off the bat. For this triangle ABC example, I know AB is 5, that is my hypotenuse. And then I can go around and say, oh, BC is 4, AC or CA is 3. And then it's going to say if it wants like cosine of Q, it wants it at angle Q. So this one might say at tangent of B. What's tangent of B? So you have to construct your angle right here at B, and then it'll be like, oh, what's the opposite over adjacent? What's the TOA? So that'll be AC over BC. Okay? And that's all there is to it. You don't have to reduce. I'm not picky on that. Number three. Number three is a problem that we haven't done yet, but it's something that we could do. It is technically a Cambridge problem, which is kind of sweet. I'll get you started on it. If you notice right here, so we have this triangle right here. We have this non-right triangle and this actual right triangle. But if you look on the very outskirts of this, we have a huge right triangle on the outside, okay? And that's where our trig functions can really come in handy, okay? So part one's asking us to find the length of BX right here, right off the bat. If I knew what this angle was right here, well, I have the hypotenuse, and I would have my adjacent side right here. So think about what trig function you can use to figure out that side length. And it also wants you to show that angle CAB. So this guy right here, angle A, basically. They want you to show that angle A is equal to the arctangent of this. I mean, we're going to have to use the arctangent, so we're definitely going to be using tangent. So as long as you use tangent of like your bigger right triangle and use your CX over your 4 plus whatever you get for BX, that'll help you figure out what it is for tangent, and then you can take the arctangent of that stuff. It's going to look a little messy, but nothing that you guys can't handle, okay? In part 2, show the exact length of AC It's 52 plus 24 square root of 3. Again, it's going to play itself out like that as long as you go through the process. One of the things I do want to touch on, though, is kind of working with radicals and factoring, or not factoring, but distributing those out. So if we do that, really, we know like these first three that I just did, 1 times this, and then, anything times 1, we're going to be fine. It's really this last one where we have 2 square root of 2 times 2 square root of 2. Okay. Just as a reminder, when you do this, I would multiply these guys first, like the outer coefficients, and then multiply your radicals. I kind of treat my radicals kind of like variables in a sense. I know they're not variables, but that's kind of how I treat them. I treat them as their separate entities, so I get 2 times 2 is 4, and then square root of 2 times square root of 2 is just going to be times 2 for that. So I'm going to get 8 when I multiply these guys out. Okay. When you do square root of 2 times square root of 2, you can combine them and make it square root of 4 underneath, right? Or if it was like square root of 3 times square root of 6, you can make that square root of 18, right? But square root of 4 obviously is just 2. So that's where I came up with that. Okay? And you're going to have to manipulate those at some point on number 3. Okay? Let's go ahead and turn the page. Number 4 might look pretty familiar. I don't think we did part 2 in showing that the perimeter of this entire shape is this guy, but it's going to work itself out once again. But as long as you can get one of these side lengths, it's going to be the same side length for all these, and then you're just tasked with having your OD and your OA, but your OA is given to you, and you'll find OD in part 1 anyway, okay? So as long as you get part 1 done, which you've done before, I think you could do part 2. Let's look at exercise 7b. These are the trig identities. These are giving us a hard time, okay? I'm going to write these trig identities out for us. Okay, we know our Pythagorean identity, the sine squared theta plus cosine squared theta equals 1. But I'm also going to write the alternative versions of that because it's just not very clear just giving that one. So what I could do is, and we're running into these a lot, if I have sine squared theta, that's equal to, if I subtract cosine squared theta from both sides, I end up with 1 minus cosine squared theta. So anytime I'm like given something with sine squared theta and they're like, I want you to write this in terms of cosine, or if you're like doing an identity and you think it's a good idea to turn it in terms of cosine, and you have sine squared theta, you can do this, okay? And same thing with cosine squared theta. That's going to be equal to 1 minus sine squared theta. Those are our 3 trig identities for the Pythagorean identity. And then, of course, I'm not going to forget our good old pal, tangent, which is equal to sine theta over cosine theta. Okay? And you can use these, I'm going to say these 4 identities in tandem, but it's really just 2 identities. We'll call it 4, though. Okay? And yeah, I just want you guys have seen all these problems before, except I think this bottom one is the only one that's new. So this is just additional practice on this, okay? Let's look at exercise 7c, solving equations using trig graphs. So in this lesson, we seldom use the trig graph, right? Like we'd make it to just see what's going on, but we really didn't have to do a lot of graphing. We did more graphing in this last lesson that we just did, okay? Really the key thing from this one are reference angles and how to use them to solve these equations. This is something that we struggle with still. So let's talk about this for a second. We're going to assume that alpha, or we'll just call it A, is the reference angle. And this theta is our terminal angle, so wherever we're ending up on our unit circle, okay? To find the reference angle is always in quadrant 1. It's basically the angle that in quadrant 1 that gives you the same value as your coterminal angle as well. So for example, if you had like 45 degrees, 135 degrees would also be, they would give you the same value if you took the sine or cosine of that, because 45 and 135. 45 is the reference angle of 135 degrees, okay? And really, as long as we are in quadrant 1, our terminal angle and our reference angle are always going to be at the same spot. I want you to realize, though, that this theta is not a coterminal angle. It's not ending at the same spot as the reference angle. It's just where it ends up in general on the unit circle, okay? So that means if I had like a terminal angle of 220 degrees or something like that, and I wanted to find the reference angle, well, 220 degrees, I know that's in quadrant 3, so I'm going to take my 220 degrees, that's my theta, I'm going to subtract 180 degrees, and then I'm going to end up getting 40 degrees, and that is my reference angle to 220 degrees. Okay. So why are reference angles important? Well, let's just take a look at this first example for part 1. Okay. For cosine of x. So I'm going to go to Desmos real quick, and I'm going to put on the cosine graph for us. All right. So our problem was cosine x equals 0.5. So I'm going to put y equals 0.5 on there. And if you look on our graph, so we're going from 0 degrees to 360 degrees. That's where my computer screen ends. We are actually getting to answers right here. We get 60 degrees and we get 300 degrees. Okay, if we think about it on our unit circle, 300 degrees is in quadrant 4 and 30 degrees is in quadrant 1. Cosine is positive. It's positive in quadrant 1 and quadrant 4. So that makes sense why those two angles are giving us that value. But let's just pretend we didn't know that for a second. What would we do? What if we what if we had something like this, right? Something a little nastier, right? Well, first move is going to be taking the arc cosine of that value right there, right off the bat, or the arc tangent of this value, right? So we'll do the arc cosine of 0.5. We're going to just leave it in degrees. And that is going to spit out 60 degrees in your calculator. Cool beans, right? So 60 degrees makes sense. Quadrant 1, it's going to be positive. But if we look at our unit circle, we know it's also positive in quadrant 4. So what I do is I take this guy right now. And this is like my terminal angle, you could say. I'm going to plug this guy in. I'm going to plug this guy in for theta right here, okay? Because in quadrant 1, the alpha is right now equaling theta. So I'm going to plug the theta in right here, and my alpha is going to give me 360 minus 60, so I get 300 degrees. That is also where I get my 1/2 from. So if you take the cosine of 300 degrees, you should end up getting your 0.5 back. Okay. And right now we are working with this domain right now. So really the period of the functions for sine and cosine really comes in handy because we can get terminal angles or coterminal angles. So if I did 60 degrees plus 360, I'm at 420 degrees. If I do cosine of 420 degrees in my calculator, I also get 0.5, right? Because if you go in a full circle and you just end up back in your same spot, you're still getting the same value. You're just a bigger angle measurement. You went around more times. You can go around forever and ever, right? Really, the tangent period is what's super, super useful for tangent. Tangent, you can just add 180 degrees and it'll or subtract 180 degrees depending. And as long as you end up between this domain, you should be pretty good on that, okay? Let's look at 7D for a second. For circular measure, this is really converting stuff from degrees to radians and radians to degrees. If we're going degrees to radians, we're going to multiply by pi over 180. That's our conversion. And then if we're going radians to degrees, I multiply 180 over pi. There's a little confusion on this. A lot of students are saying like they'll if they're going from degrees to radians, for example, so they're like 45 degrees times this, and then in their calculator they're very concerned about making sure they're in radian mode all of a sudden, or they're in degree mode. It has no effect on this at all. We are already converting degrees to radians by multiplying by this. We don't have to do anything with the calculator. What we need to do with the calculator is, well, if I have a cosine of 30 degrees, I'll use cosine of 60. That's probably easier. Cosine of 60 degrees, I get 1/2 back. My calculator is in degree mode, so it's reading this as 60 degrees, not as 60 radians. That's the only reason you need your calculator to be in a certain mode. Because now, if I change my mode to radians, and now all of a sudden I try to do cosine of 60 degrees, it's going to read it as 60 radians, and I'm not going to get even close to what I had. I have to put it as cosine of what that would be in radian measurement, which would be pi over 3. So I do pi divided by 3, and it'll give me 0.5 back. Okay, so it only matters when you're taking the sine, the cosine, or the tangent of something. Okay, that's when it matters. This, you don't need to change any settings in your calculator. You just need to multiply. Okay. Number 3, okay, notice our domain is going 0 to 2 pi. So you can work in degrees, at least for the time being, and get your degree measurement. So you can take the arc sine of both sides here, and you can get the degree measurement for x, and then you can, go through the reference angle thing and find, oh, where else is sine negative, and then use those equations to help you. Just make sure, because this is in radians, that we are going to convert back to radians. Okay, convert answers to radians. And leave your answers as multiples of pi. Okay, so don't reduce it, or don't simplify it to a decimal, but you can reduce your fraction. Leave it as a fraction. Do not simplify it to a decimal. Okay, get practice doing that. And finally, exercise 7E, one of the more recent ones. Let's get down all of these formulas that we're going to need. And I gave you just 2 problems. One of them we're going to do, and so you only have one more that you're going to have to do on your own. They're both Cambridge problems, actually, and they're very similar to each other. Our law of sines, that would be angle or sine of A over side A is equal to sine B over side B, which equals sine of C over side C. They're all related to each other. It's all one big ratio, okay? The law of cosines. This could be C squared equals A squared plus B squared minus 2AB cosine of C. Whatever angle that that's associated with the side length, that's the one we're going to use. The area of triangles, that is 1/2 AB sine of C. Again, if I'm using a different angle, like if I'm using sine of B, then this would be 1/2 AC sine of B. So you use the 2 sides that are not associated with that angle when you're using the area of triangles. Okay, and the area of a sector, we know that is 1/2 r squared theta, and the arc length is just r theta. All 5 of those, we may or may not need to use them. We're definitely using the area of a sector, though. That is definitely standard. We're definitely using arc length. The other 3, we'll see. Okay, it's from the page. We're going to do this first example together, and this second example, I'm going to give you a chance to just try it for your homework assignment. It's very similar to this first one in terms of setup, in terms of how you solve it, in terms of just skill set. I think these are great together, so let's run through this first one. Okay. Number 1, in the diagram OAB is a sector of a circle with center O and radius 12 centimeters. The lines AX and BX are tangents to the circle at A and B respectively. Angle AOB is pi over 3 radians, or 1/3 pi radians. Okay, I know it's hard to see right there, but it's 1/3 or pi over 3 radians. Okay. We're first tasked with finding the exact length of AX. This guy right here says give your answers in terms of square root of 3. All right, well, let's try to do that first. Now the hardest part with both of these is the setup, okay? We need to find this AX side, but if I looked at like the arc length, that's only this arc length from A to B. The area of the sector is only going to capture everything that's not shaded, so it's going to ignore the shaded part. So what do we do here? Okay. Well, what we can do is we know that these guys, it said AX and BX is tangent to the circle. So what that means is if I have something like a circle and I have a tangent line, so it's just touching the outside right here, basically what I could construct right there, and I guess it'd probably be easier if I did it like maybe like right there. We're kind of making like a bisector, so we're kind of being able to make like a 90-degree angle right here. If I look right here, it bisects kind of as a right triangle, right? And maybe it's starting to look like it a little bit more. This one too, right here. Because what I can do is I can take this angle and I can just cut it in half, and now I have two right triangles to work with, which is pretty sweet. Now this turns into just a normal trig problem where I need to find this AX side. The only thing is we split our angle in half. So we were at pi over 3. I'm going to just multiply by 1/2. So we're at pi over 6. And we're going to work with that as our angle measurement, okay? This is pi over 6, and this is also pi over 6. The whole thing is pi over 3, okay? Well, we know that this side is 12 centimeters, and this is like part of our sector, right? It's the radius, so this side is also 12 centimeters. All right, and now I got to think about this. I have an opposite over an adjacent side. So I'm going to be using tangent. I'm going to use tangent of pi over 6 equals opposite, so AX over 12. And so if I multiply both sides by 12, 12 times tan pi over 6 is going to equal AX. And if you don't remember what pi over 6 is, first you can convert it to degrees. So tangent of 30 degrees if you want to. And if you don't remember what tangent of 30 degrees is, you can use that chart that we had at the very beginning. I'm going to actually rely on the fact that tangent of pi over 6 is the same thing as sine of pi over 6 over cosine pi over 6, because I'm really comfortable with those. I use those more than tangent. So sine pi over 6, that's sine of 30 degrees, that's just 1/2. Cosine of pi over 6, cosine of 30 degrees is square root of 3 over 2. And so if I want to simplify this, I'll multiply the top and bottom by 2 over square root of 3. That'll cause the bottom to cancel out, and now I can just focus on the top. The 2's are going to reduce to 1, so I get, for tangent of pi over 6, I end up getting a value of 1 over square root of 3. And 1 over square root of 3 is the same as square root of 3 over 3. If I multiply the bottom and the top by square root of 3. Okay? That was a lot. So 12 times square root of 3 over 3 is equal to AX. And I can reduce this. This is 1, this is 4, so my answer is 4 square root of 3. And we're working in centimeters. Okay? So that's my side length right there, 4 square root of 3. That would also be this side length as well if I wanted to write that down. Part 2. It's now asking me to find the area of this shaded region right here, this stuff right here. Okay. What we can do with this is we know that the triangles capture that shaded area, right? But we only want the shaded area. I also know that the sector area is going to capture just the white part right here, the clear part. Okay. So if I got the area of my triangles, the area of my two triangles, and I subtracted my area of my sector, I'm going to end up getting the area of the shaded region, which is sweet. How do I get the area of this triangle right here? Well, I only need the area of one of them because I know that they're going to be the same, so I can just multiply by 2, whatever I get. Again, I'm working with a side length of 12 centimeters, and this is 4 square root of 3. Again, I want to use this formula 1/2 AB sine of C. to help me get the area of a triangle. I have side length A, I have angle C, but I need side length B. So I got to use Pythagoras Theorem to help me out. So let's do that to find a side length B right here, okay? So Pythagoras Theorem, we're going to have 12 squared plus 4 squared to 3 squared equals B squared. So this is going to be 144. This is going to be plus. Now, when I square something, like a square root thing, I have to distribute it, essentially. It's like the power rule with exponents. I got to take it to both. So this is 16 times 3, which is just going to give me 48, and that equals B squared. And so 192, or the square root of 192 is what B equals. Square root of 192. So now I can actually use this formula to get the area of my triangle. So I have 1/2 times 12 times square root of 192, and then it's going to be times the sine of this angle, pi over 6. Okay. Well, I know half of 12 that's just 6. Square root of 192. Let's go back to part 1, what it says for. It says, give your answer in terms of square root of 3. Okay, so I need to split this guy up. It's not good enough to just reduce it and simplify it to, or not reduce, I keep using that word. It's not good enough to simplify it to a decimal. We're not going to do that. We're going to split this guy up, okay? So think, what are two numbers that multiply together to give me 192, and then can I take the square root of one of those numbers? Well, I'm obviously going to be using square root of 3. So 3 times what gives me 192? Let's see. 192 divided by 3. Oh, I get 64. So I could split this guy up as 64 square root of 3. Well, we know what square root of 64 is. That's 8. Okay? And so we have 6 times 8 times square root of 3 times sine of 30, which is 1/2. And if I multiply everything, 48, I'm going to divide by 2, that's 24. So 24 square root of 3 is what the area of one of my triangles is. So to get both of them, I got to multiply by 2. So I get 48 square root of 3 is my area of my triangles. We're almost done. I got to get the area of the sector. That's 1/2 r squared theta. So that's 1/2 times 12 squared. And my theta, I'm working with a sector, so it has to be in radians. And it's not pi over 6. I'm getting the area of the sector, so that is my original pi over 3. And so I get 144 divided by 2, divided by 6 actually. So 144 divided by 6, I get 24 pi. It's good that I'm doing this again. Going back to this, give your answers in terms of pi and square root of 3. So now I do 48 square root of 3 minus 24 pi, and that's my area, guys. It wanted just the area in terms of that, so that is my area. Technically, it's centimeters squared. Okay. I know that looked like a lot, but to kind of get you started on this one, once again, it wants you to first solve. It wants you to find this angle right here, which you can find because you have the arc length. It wants you to find the length of PT, which is very similar to finding the length of AX. So if you notice, you can get 2 right triangles again, and then you can also find the area of the shaded region, because you know the area of those triangles minus the area of the sector will give you that area. This is Mr. Knight signing out. I hope that was helpful.